Go ahead. Okay, so guys, I typed in x to the fourth. What do you notice? That x to the fourth looks exactly like a parabola. Here, let me go ahead and type in a second degree. Look at that, guys. Almost exactly like the fourth degree polynomial, okay? So now I'm gonna go ahead, remember earlier I said, as you go further into the higher degree polynomials, their graphs, they start mimicking each other. They start resembling each other, okay? So in the case of this one, this is the first problem we worked on tonight, -6. Notice guys, as I type in these values, the numbers are changing. Look at that -6, what it just did to the graph of this fourth degree polynomial. It brought down, it changed the coordinate of the vertex down to 0, -6. So that's what you call, guys, a vertical translation, okay? And then I am going to add the x squared on here, okay? And by the way, how am I doing the power? I'm using my delta, the same delta that you guys have on your calculator, the caret, okay? So I'm gonna hit the x squared. Now guys, notice, what do you notice here? This is a beautiful quadratic, fourth degree polynomial. And it's got how many turning points? It's got, here, let me zoom out a little bit. Okay, look at this, guys. It's got 3 turning points. One of the things I mentioned to you earlier was the number of turning points on these graphs, guys. The number of turning points is at most the degree -1. So if you do 4 - 1, you will notice there's 3 turning points on here. One is at 0, 0. Here's another one right here. I like using the Desmos emulator because you can actually go on the calculator and the calculator will tell you exactly what the points are. Okay, that's not the same thing with your regular graphing calculator. On your regular graphing calculator, you have to use the trace feature, and most of the time it's not very accurate. This one is way more accurate, okay? Now, additionally, if I go to the x-axis, guys, those are the x-intercept. Look at this. Even though they're not exact values, but it's giving me a very accurate figure of what the x-intercept is. So one of them is 2.449, and then the other one right here is at -2.449. By the way, this also is telling us that this graph is symmetric with respect to the y-axis. So yes, this graph is symmetrical. By the way, when a graph is symmetrical with respect to the y-axis, it means that it's an even function. What you see on the left is what you're going to see on the right. So the right is reflecting the left and vice versa. And then guys, of course, there's a 0, 0. Now, another point I could make here is the end behavior, okay? Look at the end behavior. On the left side, guys, the graph is rising up towards positive infinity. On the right side, the graph is rising up towards positive infinity. There's 2 end behavior questions on the test. So when the question comes up, what does the end behavior of this polynomial look like? You can type it into your graphing calculator and look at the graph on the graphing calculator. It will tell you which direction your graph is going based on what's happening on the screen here. So on the left side, as x is decreasing, y is increasing. So it's rising on the left. On the right side, as x is increasing, y is also increasing. So it's rising on the right as well. So it rises left, rises right. Even functions, guys, either both ends go up towards positive infinity or both ends go down towards negative infinity. That's the even functions. Okay. Now, I'm still not done typing the problem, so I'm going to go back over here and continue typing the problem. -8x. You see how the graph is changing, guys? And then plus, did I put the plus? No, that's not a plus. Plus 24. Shazam, there's my graph. Now, earlier, Jessica said, you know what? I typed this problem into the calculator, and I'm only getting one answer, and that one answer was -1. Now, and I told Jessica, listen, what's the graph doing? I asked her actually, and she said, the graph looks like it's touching, it's bouncing at x equals to -1. This is what's happening with this one, guys. Notice it's sitting on the x-axis, it's touching the x equals to 2, okay? It is not going straight through the x-axis. So when you see a graph just bouncing or touching at an x-intercept or a 0, we say that this 0 has an even multiplicity, as in 2, 4, and so forth and so on, okay? Since this is a 4th degree polynomial, you would say the multiplicity is 2. Yes, absolutely. Another rule we didn't talk about was Descartes rule of sign. The Descartes rule of sign is worth mentioning, but ultimately, guys, it's about finding the zeros of the polynomial. So guys, what did this just help us find? It helped us find one of the zeros, but because it is touching at that 0, it actually helped us find 2 zeros of the polynomial. In this case, positive 2. And you could use it twice with the synthetic division. That's how powerful these graphing calculators are. Okay, so let me go ahead and go to another one, guys. This was the second one we did. And the second one we did was x to the 4th. Where is it? Oh, here it is. X to the 4th. Okay, and minus, okay, you guys are not asking any questions. 2x to the 3rd. You should be asking questions about this because I know the graphing calculator is such a hassle. So ask questions, guys. Minus 5, x to the 2nd. Okay, guys, watch how the graph is changing as we type in these values. And then plus 8x, and then plus 4. Shazam. There we go, guys. There we go. 4th degree polynomial. Now, if you recall, when we did this, we had 2 real zeros. One of them was at -2. That's right there. The other one was at +2. Those are 2 real zeros. And then we had 2 irrational zeros. What are irrational zeros? Those are the zeros with repeated decimals. Like this one right here, -0.414. And then the other one is right here at 2.414, guys. That's how powerful this is. But if you're doing this problem on your tests, on my math lab for your assignments, you cannot be putting the decimals in there. Yeah, you have to plug in the answer as a simplified radical. Yeah. All right. You guys are not asking any questions. Let me see. My calculator says 2.5. Would I get it right on the test? Still, I know yours says 2. No, it won't accept the 2.5, as I just said, because they want the answer in simplified radical form, not a decimal. Remember, my math lab doesn't like the decimals, okay? Now, here's the last question we did today. And let me see here. By the way, guys, I haven't been emphasizing the max and min values. I'll do that with this problem, okay? X to the 5th power. Oh, no, 4th power. You know what? I'm going to do an x cubed 1, too. Hold on a second, guys. X to the 4th power minus 2 x to the 3rd. Ooh, Shazam, that's horrible. I forgot my minus sign. Okay, minus 2x to the 3rd. And then we have plus x squared. It's a pain typing it in here, but it's worth it, guys. Plus 12x. And guys, ask questions. If you have a calculator and you don't know how to operate it, ask questions. And I'm only using this one because I don't have my regular graphing calculator in front of me. Okay, that's why I'm using this, and I can't download one of those graphing calculator emulators, the regular ones, okay? So guys, look. Remember how Jessica said, wait a minute, I'm only seeing one solution. She was absolutely right. Why? Because the graph is only intersecting the x-axis just once. Where? At -1, 0. What is the graph doing at -1, 0? Is it crossing or is it touching? It is touching. Why? Because the multiplicity is even. And since it's a 4th degree polynomial, we're going to assume the multiplicity is 2. By the way, guys, look at this. There's your y-intercept right there. Shazam. Okay. Additionally, guys, this point right here represents a minimum value. So this graph has a minimum. What's the minimum value? 0. Yes. All right. Now, let me show you something else I want to go ahead and mention. Okay, here's another one, guys. And this one, I'm primarily mentioning it because of end behavior, okay? So it's going to be a negative x to the 4th power. What do you notice? The graph, guys, is an even function. And both ends of the graph, they're going down towards negative infinity. They're approaching negative infinity, okay? So that negative leading coefficient changes the direction of the graph, allows the graph to reflect over the x-axis. See, if I take the negative away, look at that. If I put the negative back in, look at this, guys, okay? So next, I want to go ahead and plus 4, x to the 3rd, x to the 2nd. Let's see here. Oh, all right, there we go. So guys, there's the graph. So some of the things I want to highlight on here. First and foremost, we talked about the end behavior, the zeros of the polynomial. If a problem asks you to find the zeros, the roots of the polynomial, guys, you can type it in here and look at that right there. Wherever the graph intersects the x-axis, that's a 0. So here's one at -2. Here's the other one at 0. Here's the other one at +2. If you on your regular graphing calculators, your TI graphing calculators, you can't tell what they are, go to the table, hit table. Table's on the top right side of the calculator. If you hit table, wherever y is equal to 0, the corresponding x would represent the 0 of the polynomial. Additionally, guys, right here, we have a maximum value at y equals to 4. This also represents a maximum value at y equals to 4. Relative max. But because it's the highest point on the graph, we can also use absolute max. That will happen in pre-calculus. They will talk about that. And then over here is your relative min. And this one is a relative min. You cannot say it's absolute because it's not the absolutely lowest point on the graph. These are absolutely the highest points on the graph. But this one is only relative to the points around it. So you have a minimum value at 0. Okay? All right, guys, so that's another 4th degree polynomial. As I promised, I was gonna do a 3rd degree polynomial with you so you can see what the 3rd degree polynomials look like. So let me go ahead and do a 3rd degree polynomial with you. And then I'm gonna do one more and we'll be done with the graphing calculator session. All right, guys, I'm looking for a nice 3rd degree polynomial. Oh, you know what, let's go ahead and do this one right here. X to the 3rd. Let me see here. Okay, guys, so look at that. X to the 3rd, what do you notice about the graph? One end of the graph is going up towards positive infinity. The other end is going towards negative infinity. When you're looking at the odd degree functions, you have to consider, guys, slope. Positive slope rises to the right. Similarly here, you have a 3rd degree function. It's going to rise to the right. So as the x values are increasing, the function increases towards positive infinity. As the x values are decreasing on the left, the function decreases towards positive infinity. Another way to describe this graph for end behavior, guys, on the left side, you say that the graph falls towards negative infinity. And on the right side, you say that the graph rises towards positive infinity. Now, what would happen if we have a negative leading coefficient? Look at that, guys. Did you see it? Yeah. So negative leading coefficient, what does it do? It changes the direction of the graph. So on the left side, it's rising towards positive infinity. On the right side, it is falling towards negative infinity. So guys, listen, again, think for the odd graphs, think of negative slope, positive slope, all right? Now, remember how I told you that these graphs, once you pass the 3rd degree polynomials, they start repeating. Well, let's look. Look at this. Guys, that's exactly the same thing. Almost exactly the same thing. It's just a different graph. It's the 5th degree, okay? So what if I were to remove that negative? Look at that, guys. Yeah. So once the graphs pass, once the polynomials pass the 3rd degree, they start repeating each other, okay? They start mimicking each other. So let me go ahead and finish writing out this function right here. X to the 3rd plus 2x to the 2nd. All right. And then it's going to be a minus 2x, and then minus 12. And guys, there we go. That's a third degree polynomial right there. All right. Let me see. Can I adjust this just a little bit and see if this is going to help me just slightly? Let's put a 6 here and see what happens. Now, the reason why I just did this, guys, is to reflect what you're going to see on the assignment. One of the assignments will ask you to graph a third degree polynomial. And for that third degree polynomial, guys, it has 3 zeros, 3 real zeros, and 1 intercept. They will ask you to find the intercept. So what intercepts are they talking about? They're talking about the y-intercept. This one is at 0, -12. And then all the x-intercepts. Ooh, these are not precise. Ooh, they are not precise, guys. They are not. Okay, let me make this a little bit more precise. Let's go ahead and do, let me see, x plus 2. Let's make this a 4. And then let's make this an 8 over here. Let's see. All right. Well, that's better. -2. And then there's your positive 2. There's your y-intercept right here at -8. Guys, listen. The graphing calculators actually helps you to do your work more efficiently. That's the purpose of these graphing calculators. And then one last thing I need to say about the graphing calculators is when we're graphing, guys, the rational functions, because that's going to be the next, I don't know how I'm going to type in a fraction in here. I haven't played with this one in a while, guys, but I'm going to play around with it anyways. When we're graphing the rational functions on the graphing calculator, I'm talking about the fractions with variables in the denominator. Yes, you can graph them in there, but you have to be very careful. So if I had to graph x minus 2 in the numerator over x squared minus 1 in the denominator, guys, let me go ahead and show you how you would do it. First, the numerator, you would enclose it inside a set of parentheses, as in x minus 2, okay? This would be the numerator, and then close it off with a parentheses. Now, we're going to use divided by. Where's the divided by? Right there, okay? And then you're going to type in your denominator. And we're going to include, well, actually, we don't even have to enclose it now because we already have the numerator. So we have x squared in the denominator. And then we're going to minus 1. All right, guys. Do you see the graph? Now, I don't want to get too far into this lesson, which is what we're going to cover next time. But first, I want you to notice, guys, along the x-axis, the graph looks like it's kind of flatlining right above the x-axis. By the way, that's coming up next week. We're going to talk about that. Actually, you know what? I'm going to talk about it in my next class on Monday night, and I'll send you guys the video. This represents a horizontal asymptote. An asymptote is a line, vertical, horizontal, or oblique asymptote that a function approaches but will never get to because it's undefined at that value. Now, the other thing I want you to notice is that the graph flat lines around here, guys, at x equals 2, -1, as well as at x equals 2, +1. Those values represent the vertical asymptotes, okay? And by the way, they're imaginary. That's why you're not seeing the actual vertical lines there. How do we get them? Those two values, the -1, the +1, that's what makes the denominator equal to 0. So those restricted values, those excluded values, they are the vertical asymptotes in the graph, those values that make the polynomial, I mean, not polynomial, this rational function undefined. So guys, what do you notice? This graph is defined on 3 intervals. One interval goes from -∞ up to -1. -1 is not included. Another interval is in between -1, +1. And then the third interval goes from +1 not included up to +∞. So yes, guys, you can graph these problems on the graphing calculator. You can utilize the graphing calculator effectively and be able to get through your test more efficiently. Now, the beautiful thing is normally when I do the chapter 3 test in class and it's all multiple choice, what I typically tell the students is, if you're really good at manipulating your graphing calculator, you can actually do the majority of your tasks using the graphing calculator, if you're good with it. The only way for you to be able to get good at the graphing calculator, guys, is to practice with the graphing calculator. Now, I am not one of those instructors that's going to sit there and just talk about the graphing calculator, No, 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 no. I teach you the material first, then we go on the graphing calculator and see how the graphing calculator could help us to be more efficient, could make the process more effective. Yeah. So I'm going to stop here with the graphing calculator unless somebody else has a question for me. Nobody? We're good? All right, guys, so we're going to stop here with the graphing calculator. I'm going to stop recording.